was actually an afterthought by Arrhenius. He wasn't really interested in doubling of CO2. He was actually interested in explaining the ice ages. And so he first calculated what do you get if you halve the CO2 concentration in the atmosphere, and how much cooling do you get, because he wanted to see whether this could be part of the explanation of the ice ages, which indeed it is. It is a feedback that without that, the ice ages wouldn't be so cold, and you can use that to determine how sensitive the climate is to CO2. This effect of a CO2 doubling is called the climate sensitivity, because it does tell you how sensitive the global temperature is to a change in the CO2 concentration. And the modern estimate for this is 3 degrees, rather than the 4 to 6 that Arrhenius got. But you have to you have to grant him that he didn't have a computer, and he had to do it all with pencil and paper, and also, more importantly, he didn't have access to all those data that we have now that tell us about the strength of the feedbacks in the climate system, the water vapor feedback, the cloud feedback. He had only rough estimates of these, so his number of 4 to 6 degrees is not far off what we today think is a real number, namely 3 degrees, with a remaining uncertainty of plus minus 1 degree, which is mostly due to the cloud feedback, which is still not well enough understood to narrow down this uncertainty. But there are many independent ways of determining this climate sensitivity, including from the sophisticated computer models of climate, but also from data from the Earth history. This is what has been done in my group, for example. And all these different studies, there are 13 different estimates of this climate sensitivity listed in the latest IPCC report. They all come consistently to the result that it's around about 3 degrees. So if you double the CO2 concentration, you heat the planet by 3 degrees. That immediately allows you to calculate how much warming should we have caused by now, by that increase in CO2 that I showed you. And it's slightly more complicated, because you have to take the other greenhouse gases into account as well, not just CO2. And you also have to take into account the thermal inertia of the oceans, which means that we don't immediately get the full warming, but rather we lag behind, always by a few decades, behind the full-blown warming that we will get eventually from that rise in greenhouse gas concentration in the atmosphere. But this is relatively easy to calculate on the back of an envelope, and with 3 degrees climate sensitivity, the changes in the atmosphere that we have caused up to today should have caused a warming between 0.7 and 0.9 degrees centigrade. And you can compare this is the forecast of physics, so to speak, of that global energy balance equation. You can compare that to what really has happened, and this is what the data show. They indeed show a global warming of 0.8 degrees over the last 100 years or so. And the thick line, by the way, is a trend smoothed over 15 years, and the individual dots here are individual years of the global temperature. And you can see that apart from the long-term trend, of course, there is a wiggly up and down. That's just weather. That's natural variability that you get from year to year. And 2008 happens to be a relatively cold year, which is way below the trend line. The previous years have all been above the trend line, but that's simply natural variability. I stress that because there are some people who try and read all kinds of things into this relatively cool value, but you can see here that many times in the past you get individual years that are way below the long-term trend, as you get some that are way above, like this one or 1998 here. That is just the natural variability, and you have to take the trend over a long time, like 20-year time span or so, to get a robust statistical estimate of what the trend is, and it is pointing up at a rate of about 0.17 degrees centigrade per decade. The ocean temperatures go through a similar warming, by the way, so it's not some kind of urban heat island problems with the data or so. That's also shown, for example, by the glaciers vanishing in the mountains. Clearly, glacier melt can't be caused by urban heat island. I should perhaps say why we have this funny shape of this curve. This is due to the fact that, of course, CO2 is not the only factor that influences climate, but we have the observed climate as a result of all the combined effects, like including natural variations like solar activity changes, as well as all the human-caused climate impacts, that is not only the CO2 but other greenhouse gases, but also cooling effects by air pollution, so-called aerosols, which offset some of the greenhouse warming that we're causing. And if you look at this curve, in the first, you see three phases. The first warming phase here is a phase where you have solar activity increasing as well as greenhouse gases increasing, and both of them have contributed to this early warming up until the 1940s. Then you get this plateau phase. Here solar activity stopped increasing. It actually has shown a slightly downward trend since the 1950s. And you get a big increase in aerosol pollution during this time, which led to the famous or infamous London smog, for example. Many thousands of people died from that smog until power stations were fitted with filters and the air pollution was cleaned up. And so in this phase we have basically rise in greenhouse gas concentration, but also rise in the cooling effect of that smog, and they roughly balance each other. And then the smog pollution was reduced, greenhouse gases keep increasing, and solar activity is pretty flat, slightly downward during this time, but it's too weak to offset much of that greenhouse caused warming. I put some historic dates on here. This is when Arrhenius first calculated the effect of CO2 doubling, purely academic exercise at the time. Actually, they thought it was a good thing. There were articles written, we should emit more CO2 by burning open coal mines, so that we get a nicer, warmer climate. That's what Arrhenius said. Maybe it has something to do with him coming from Sweden. He obviously didn't think through the consequences very well, sea level rise, etc., which I'll come to in a few minutes. Now, the first specific time forecast was actually made in the early 1970s by a famous British meteorologist, John Sawyer, who published in Nature an article in 1972 saying that because of the observed rise in greenhouse gas concentration, there should be a warming of about 0.5 degrees centigrade by the end of the century. And it's quite remarkable that he made this forecast at this time here, when there was no sign of any actual global warming for the past decades, quite apart from the fact that this data set, the globally compiled reliable data sets, were not available at the time. So people didn't actually know what the global temperature was doing when he made this forecast. But he turned out to be pretty right, because by the year 2000 there was indeed about 0.5 degrees centigrade of warming. In the late 1970s, the first time a major scientific organization, namely the National Academy of Sciences of the United States, warned of the impending global warming due to carbon dioxide increase. And then in the 1980s, the IPCC was founded, and in 1990 issued its first report that was here. And by now we are into the fourth IPCC report that was published last year. If we didn't have those data, we would still know that climate is warming. I mentioned it. The glaciers in the mountains are vanishing almost everywhere on the planet, with very few exceptions where snowfall rates have increased. This is a picture from the southern hemisphere. I took that in New Zealand, of the Muller Glacier. And you see where the terminal moraine of this glacier is, where it was 100 years ago. And it's basically collapsed into a puddle, little meltwater lake that has formed here. And you will find this picture all over the world. You can also see the warming from space. So if any aliens from space are observing us, they know exactly what's going on. They just have to look at the ice cap on the North Pole. This shows the sea ice cover in the polar ocean from satellite data. This picture is 1979, when we first had the satellite up, and this is 2007. So if you compare those two, you can see how much the Arctic ice cover has shrunk. And this year, in 2008, for the first time in living memory, we had the northwest passage through here and the northeast passage through here, both ice-free, so ships could simply go through there, and a German research vessel circumnavigated the whole North Pole without any problem having to break through ice. This is a time series that goes with that, and you see the steady decline of sea ice cover, and then a strong minimum in 2007, and the 2008 value wasn't much higher than that. So there is some legitimate concern that this trend is not just going to continue linearly, but it's actually accelerating, and we might see a relatively rapid end of that sea ice cover in the summer in the Arctic Ocean over the coming decade or two. This decline, by the way, is faster than predicted by any of the climate models. I mentioned that there are things that are simple to calculate, like global mean temperature, but there are things that are much more complex, like the behavior of ice, and obviously our models are not doing a very good job here, and unfortunately they have been underestimating the problem. So let's look at the future. If we accept that the climate sensitivity is about 3 degrees warming for a doubling of CO2, then you can easily calculate how much warming we expect in the future, and it mainly depends on how much greenhouse gases we will emit. And that's why there's different scenarios. They have names like A2, B1, etc. They are just different emission scenarios, so that means different assumptions about how our economy will evolve and how much in terms of greenhouse gases we will emit. In a way, these are not a forecast, and they're not called forecasts, they are scenarios, because we have a choice which one we want to get on here, because it is still in our hand how much greenhouse gas we will emit in the future. But plausible scenarios give us a warming of 3, 4, some even go up to 6 degrees warming this century, the more extreme scenarios. This, by the way, is not an emission scenario. This is called commitment, and that is if you simply from tomorrow, or actually not from tomorrow, from the year 2000, so it's already in the past, froze the amount of greenhouse gases in the atmosphere and kept them constant ever after. That just shows you how much extra warming you will still get simply from the inertia in the system, even if you had stopped the increase of greenhouse gases completely. So there's some limited amount, a few tenths of a degree of warming that are basically inevitable anyway by now. That's just the global mean temperature, and that's not telling you the full story, because there are big regional variations, which you see on this movie. This is the highest resolution climate model run by the Japanese colleagues on a major supercomputer called the Earth Simulator, which for quite a long time was the fastest supercomputer on the planet, but by now it's already been overtaken by other computers. This is the year here. Nothing too much exciting to be seen yet. You start to see the warming in the Arctic quite clearly now in this computer simulation, as it has indeed happened in the real world. But as we go further into the 21st century, you start to see some real hotspots of warming. Himalayas, for example, here. These are the regions where the snow and ice cover shrinks, and that's why you absorb more radiation from the sun and you get extra amplified heating. This is getting quite uncomfortable now towards the end of the 21st century. This scenario actually is a global mean warming of 4 degrees, so it's not extreme, it's a kind of middle of the road greenhouse gas scenario, but 4 degrees global average warming means more than 6 degrees in most continental areas. That's simply because 2/3 of the planet is covered by oceans, and the oceans have a big thermal inertia. They don't warm up as much as the continents, so don't get deceived by those global mean numbers. The global mean is made up mostly of the ocean that stays quite cool. Where we live on land, you get a lot more warming, and especially in the high latitudes in the Arctic, you have warming in excess of 12 degrees now in this scenario, simply because the ice is vanishing, and so the Arctic heats up due to the ice albedo feedback effect. Now let's talk about some of the consequences. The consequences are not mostly the changes in the annual average global mean temperature, or not even the annual average local temperature anywhere. The most effect of climate change are actually in the extremes and in other things like the water cycle, etc. The first of these impacts of climate change is the frequency of heat waves. I think to any layperson it's plausible